We're going to wrap up here chapter 10, which obviously is on our exam coming up on Monday. We just have a few more slides to finish up, and then we'll talk about next week and everything going on. So we've been talking obviously about solutions and colligative properties. Again, we finished up talking about colligative properties and the idea of what happens when we do deal with ionic solutes. So again, you do have to take the von Hoff factor into account when anything that involves any type of ionic compound. And again, it's really because it is based on the number of particles that are in that solution. So for the most part, you could just use the formula like we talked about and basically figure out I, which will be based on how many ions it basically breaks apart into. And you could basically just incorporate that into pretty much all the colligative property formulas we saw. The one that's a little bit different in terms of how you sort of incorporate the I, again, was the one we did at the very end there with the Raoult's law and the vapor pressure lowering. Again, that's sort of incorporated in the mole fraction part of that formula. And basically, you're just going to try and take the moles of your solute and in that case, and basically multiply it by basically I in that case, and you're going to add that for your total moles part of it. So we're going to finish up here, talk about a few more properties of solutions. First off, we talked a little bit about semi-pyramidal membrane. This is a membrane that allows solvent molecules and very small solute particles to sort of pass through, but large particles are sort of prevented. Kind of like in our cells, where there's basically membranes that allow certain things to pass through and certain things not to pass through. Although we can't usually see it for most part, you know, there's like holes in sort of the membrane, and it allows sort of a passageway of things that are small enough to sort of fit through the hole to go from one side to the next. Colloids are particles that are much larger than solute particles in a solution. These are really large particles like proteins and groups of molecules or ions together. Colloids are homogeneous, which, as we know, homogeneous means it's the same throughout. It mixes, so everything looks kind of the same. They do not separate out or settle out. Colloids, though, can be passed through filters like filter paper and stuff like that, but they are too big to typically kind of go through a membrane. They kind of get stuck based on size, and they're not able to kind of go through that. Another sort of classification is suspensions. Suspensions are heterogeneous type of mixtures, and heterogeneous means you do see different phases, and same thing here. Usually suspensions are really large enough that you can kind of just see it with your naked eye. They are very different than solutions or colloids, and suspensions pretty much are trapped by filters and membranes as well. So for example, if you had some water and some sand in it, for example, you could clearly see the sand there being our suspension. You can see it with your naked eye. And obviously, if you try to filter that sand through filter paper, it's going to obviously get caught on that filter paper and stuff like that. So it will not go through. Here's sort of a zoomed in of a membrane. And again, like I said, there's really these sort of channels in it that allows, you know, certain size molecules to sort of pass through. Other size ones are not able to get through there. So obviously something big like this guy right here kind of comes in, he's going to get kind of stuck there. He's not going to be able to go through, but clearly you can see something like water is freely able to sort of pass back and forth through the membranes, through these sort of channels, and really don't get caught. Here's sort of a demonstration of the three different types of things: a solution, colloid, or a suspension. Solution and a colloid, as you can see in the first sort of beaker, basically floats around. They really don't settle. Our suspension does. So again, if you kind of go back to the sand example, if you put some sand and water, which would be obviously a suspension, it will basically sink to the bottom, and you'll definitely see it sort of settle out from it. If you take that sort of beaker and then put it through a filter paper here, we can see again the solution, the colloids, will pass through the filter paper, and our suspension again will get caught on the filter paper. And over here, sort of a dialysis bag or membrane. And again, in this bag, you can't really see it, but there are little like holes that are very, very small to allow certain size particles to pass through. And we can see when we get down to here, it's really just a solution type of molecules, or even sort of the solvent going in and out, and pretty much the sort of larger molecules do get caught in that sort of bag and are not able to sort of get out. So we talked a little bit earlier when we talked about osmotic pressure, about osmosis, but officially osmosis again is basically that flow of solvent molecules from an area of lower concentration to an area of higher concentration. As I mentioned earlier, again, the idea there is it kind of wants to dilute everything down so it flows into that more concentrated area. It will continue to flow until basically, as we talked about earlier, we hit that osmotic pressure, which will stop that flow of water molecules, for example, from one side to the other, like we talked about. Again, if the water was on this side and our salt solution was over here, the water will continue to flow until it hits that osmotic pressure. We obviously saw that you could calculate the osmotic pressure earlier by really using the ideal gas law, PV equals nRT, right? Or that the pressure is equal to MRT, which is basically the same thing. The osmotic pressure obviously depends on the number of solute particles dissolved in the solution. The greater the number of molecules that are dissolved in it, the higher the osmotic pressure would be. Pure water, as I mentioned before, has no osmotic pressure. Sometimes osmotic pressure, or sort of this aspect, is also sometimes calculated through what is sometimes referred to as osmolarity. And it's basically I times the molarity, if you will, and I, as we just talked about with the von Hoff factor. So to sort of show you the difference in terms of, if you had more particles in a solution versus less particles, if we have the same 2.5 molar solution of sodium chloride versus a 2.5 molar solution of calcium chloride, if we were to compare sort of the osmolarity of each of these cases, as we talked about earlier, I in the first case would be 2. Again, given as a sodium ion and chloride ion gives us 2 for I. For our calcium chloride, we would get a calcium and 2 chlorides, which would give us an I factor of 3. So in this particular case, the osmolarity, if we calculated it for our sodium chloride, would be 2 times our 2.5 molar, would give us 5 osmolarity. If we have the same solution there, but our calcium chloride, it would be 3 times our 2.5 molar. And that is going to give us, there's 3 times 2.5, 7.5 osmolarity. So you can see that in terms of concentration, it is much more concentrated there with our calcium chloride. It has more particles floating around in there, has a greater, what's sometimes referred to as osmolarity, and would probably have a greater osmotic pressure as well because of that. And the same thing here, if we just look into our, basically this is the molarity rates. So again, the R and the T, if we had sort of under the same conditions, the calcium chloride would again have a higher value because we would have our I that would be incorporated into that one, and obviously it'd be adjusted in that case as well. Any questions on that there? Now, reverse osmosis, right, occurs when you apply a pressure greater than the osmotic pressure coming back down this way. And when you do reverse osmosis and you apply that reverse pressure, basically going to push everything back the other way. It's going to push all the solvent molecules and all that, the water back the other way. And obviously, if you have some good filters here and membranes, it's going to catch and sort of trap all the junk on the other side and kind of push all the water molecules back through, going the other way. And that's what it's sometimes referred to as reverse osmosis, which is sort of what we see here. Kind of the water goes into the brine solution, which is like a salt solution. Again, it stops at that osmotic pressure. Applying that reverse osmosis or more pressure is going to basically send all that water molecules back the other way, and it's going to keep all this sort of stuff you may not want over on this side and sort of purify it, if you will, in that sense. Last couple of things here we're going to talk about is different ways that you could classify solutions. There's three different classifications for solutions. One is isotonic, one is hypotonic, and one is hypertonic. Isotonic is basically solutions that exert the same osmotic pressure as body fluids. Those are typically what IV solutions are. So they don't give you an IV and ruin and give you more problems. But the result of that isotonic solution is essentially if you had, say, a membrane or even like a red blood cell, which is a common sort of example, what you would have is the flow of sort of by osmosis of water and solution going in and out of the cell would basically be equal to each other. So you have kind of even flow coming in and out of the cell. Obviously, that's not going to cause any type of damage to your cell. Now, if you happen to have a hypotonic solution, hypo means less than, and that means that the solution outside, for example, of the cell or the membrane is actually going to be a lower concentration than inside. So what happens, for example, if we do that and we put, say, oh, we'll go with our red blood cell here, and we put it into a hypotonic solution, outside of the cell is less than inside of the cell. So through osmosis, what will happen is all the water outside of the cell will decide we need to rush into the cell to sort of dilute it down. The process of that is obviously the cell is going to take on a lot more water and solution. It's going to start to swell, which is probably not so good, and it will probably burst, which is known as hemolysis, and obviously not a good situation in that particular case. So by the process of osmosis, everything's going to flow in. The cell is going to act really as like a receptacle for all that solution coming in to try to dilute it down. Opposite of that is a hypertonic solution. Hyper means more than. So that means, for example, if we use our red blood cell example, outside of the cell is actually more concentrated than inside of the cell. So what's going to happen to our red blood cell and say this particular situation is through osmosis, it's going to decide that outside of the cell is more concentrated than inside. We want to dilute down everything that's outside of the cell. So all the sort of water or solution inside of the cell is going to exit the cell in a process to try to dilute down the outside solution. And that's going to cause, again, not a good situation. That's going to cause the cell to start to shrink and go through crenation and not be such a great deal. So the process of osmosis, it happens a lot. And depending on sort of the situation, it could be a good thing or a bad thing in this particular case. How do we know what is sort of an isotonic solution and not an isotonic solution? So there's typically two sort of groupings of solutions or two types of solutions that we think about. One is a 0.9% mass to volume sodium chloride solution. So a 0.9% sodium chloride solution or saline solution is considered, could be an ionic solution, really, any type of ionic solution, but most of the time is sodium chloride. Is considered isotonic. So if you have some type of membrane or something like that in a 0.9%, you're all good. Again, we're going to have kind of equal flow in and outside because there is equal pressure inside and outside of the cell. Also, 5% glucose is considered an isotonic solution. So a 5% glucose solution is considered isotonic as well. So again, it is as simple as anything being higher than those numbers would be obviously a hypertonic solution. Anything lower than one of those two numbers would be a hypotonic solution. And again, we get the flow in and out basically because of the difference in osmotic pressure between the cell inside and outside. Kind of like yesterday when we lifted up our kind of tube there when we were done with the experiment, right? With the tube sort of in the solution, right? The pressure was sort of equalized in a sense. When you lifted it up, obviously you released the pressure, right? Outside, and it started to drop out all the solution that was inside your tube as well. Any questions on that there? All right, so take some better pictures. So here's just some pictures of that. Again, it's a red blood cell isotonic solution. Looks like a regular donut. Yes, equal flow in and out. Here's our hypertonic solution where everybody's going to rush out, gives us our donut holes. And over here's our jelly donut and our hypotonic solution where everything rushes in and it's eventually going to pop. Why don't we try some here? Is it hypo, iso, or hypertonic? And will it swell or shrink? If we take a red blood cell and put it in a 1.5% sodium chloride solution, a 2.5% glucose, a 5% sodium chloride solution, if we put it in some pure water, and let's do a 0.9% sodium chloride solution. All right, so for each of these cases, what type of solution are we dealing with, and will it swell or shrink, go through hemolysis or crenation? Okay, let's take a look. So first off, isotonic, again, are the two important numbers here, 0.9% sodium chloride or 5% glucose. So those are really the numbers we want to sort of compare everybody to. So if we start with 1.5% sodium chloride, that obviously is greater than 0.9%. That would mean that this would be a hypertonic solution. That means that outside of the cell here is greater concentration than inside, and that's going to cause all the sort of water and solution to run out of the cell in an effort through osmosis to sort of dilute it down, and we would think that it would shrink and go through crenation. Any questions on that one there? 2.5 is less than 5% glucose, so that would be a hypotonic solution. So opposite here, we would actually have less concentration outside of the cell than inside. That means in this case, everybody's going to rush into the cell, and that should cause the cell to start to swell and eventually burst, which is hemolysis, and should swell in that case. 5% sodium chloride, it is 5%, but that's not glucose, it is sodium chloride, so that definitely is going to be more than 0.9. So once again, this would be a hypertonic solution, which again would cause everybody to rush out of the cell and start to shrink. 0.9% sodium chloride is exactly an isotonic solution. So this would be isotonic, and really the cell will be okay. Nothing's going to happen. It's not going to shrink, obviously, or burst. You'll have equal flow of sort of solution in and outside of the cell. How about water? Water would actually be a hypotonic solution, as water has no osmotic pressure, which means water actually would be less pressure than the cell. That means outside the cell is less concentrated than inside of the cell. So we're actually going to get things to rush in. So one of the cases where water is maybe not a good thing for your cells, we will have everything rush in and we'll start to swell and start to burst there and go through hemolysis. So again, the 0.9% sodium chloride or any type of saline solution, ionic solution, 5% glucose are your isotonic solutions, and those are the ones you want to remember and sort of compare things to. Any questions on that there? There's that. Lastly, dialysis is a process similar to osmosis. Dialysis allows small solute molecules such as ions and molecules to pass through, but does sort of prevent larger ones like colloids to sort of pass through. So sometimes dialysis is used in sort of research. For example, if you're maybe working on some type of protein and you want to sort of get your protein into the same sort of environment, say pH environment as maybe in the body and stuff like that, you can put your protein into a dialysis bag and put it into a buffer of a solution that's like at the same pH and let it kind of sit there for a while. And that would obviously simulate the same type of conditions that it would be, within the body. Our body also does dialysis, right, to get rid of waste products, right, through kidneys and all that kind of stuff, to sort of get rid of the stuff that we don't want. Obviously, when people have problem doing that, they get a buildup of all that sort of waste products and they can't filter it out of their body, basically. So they have to do dialysis, obviously, through a machine to help them do that. Here's a dialysis bag. And again, you can see it's going to allow really those sort of solvent molecules, small molecules to move through. But if you have something like proteins or something like that that you're working on, you just drop them in the bag, and they basically will get the environment, but they obviously will not escape the bag. And then obviously you could go and do whatever more you would like to do with your protein in that case. Any questions on that there? All right, that wraps up chapter 10, I think.